A brief explanation of magnetic amplification and neutralization. To the left, you see a coil of wire wrapped around a piece of low-carbon steel. The coil is wired so the face is the north or positive side, right here. When electricity is applied, it becomes an electromagnet, the magnetic force of which can then be measured. To the right and attached to the electromagnet core is a permanent magnet. But for this demonstration, I'm using a piece of aluminum. If you're not experienced in handling powerful magnets, don't do this. Now I repeat, if you're not experienced in handling powerful magnets, don't do this. The north side of the permanent magnet, that's right here, is attached to the south side of the electromagnet. The magnetism travels from the permanent magnet through the core of the electromagnet, therefore making the core part of the permanent magnet. At this point, and without any voltage applied, you can then measure the strength of that permanent magnet. When DC voltage is applied to the electromagnet, the strength of the combined magnetic forces can then be measured. It will result in an amplification of the magnetism, in this case about 1.6 times the force of the permanent magnet alone. All that's needed to neutralize the magnetism is to simply reverse the polarity of the electromagnet. The total magnetic force will be near to zero. Depending on the size of the coil and permanent magnet, the total force produced will be many times greater than that of the electromagnet alone. For example, if the total force, let's say 21 pounds, minus the near to zero number, let's say 1 pound, then the total net force is 20 pounds. Divide that by the force of the electromagnet alone, let's say 1 pound. 20 divided by 1 equals 20. Out of the 20 pounds of force produced, only 1 pound was produced by electricity. Magnetic amplification and neutralization may have many applications. I think a motor would make a good demonstration. An armature, that's the rotating part of a motor, generally looks like this. They're round, in a complete circle, having no ends. Using magnetic amplification and neutralization, the same size armature would look somewhat like this, having 2 arcs or more. The rest of the armature could be made of a non-ferrous metal or plastic. The armature on our prototype motor consists of 2 arcs and not a complete circle, as is the usual case. The armature on our prototype motor consists of arcs and not a complete circle. What you see here is a device to demonstrate how magnetic amplification and neutralization works. Note it only has 1 arc. It starts here and ends here. I'm going to demonstrate something I call magnetic lockup. It's the one thing that has to be overcome. Note with no permanent magnet attached and no voltage applied, there's no magnetism. I've used this special tool to attach the permanent magnet to the coil. Now don't try to do this if you have no experience with powerful magnets. It's very dangerous. I repeat, don't do this if you have no experience with powerful magnets. It's very dangerous. Here we have the coil, or the electromagnet, and here's the permanent magnet. Without any electricity applied to the coil, or the electromagnet, I'll first demonstrate the intensity of the magnetic lockup with just the permanent magnet alone. You can see how it's attracted at this end of the arc, and it'll come around and be trapped in between here. It can't escape this end. For this size coil combined with this size magnet, it takes 36 volts for the magnetism to completely neutralize, or simply have no effect at the face of the electromagnet. Now I'm going to turn the power on to the electromagnet, and you can note the increase in intensity of the magnetism, but we'll still have the magnetic lockup. You're going to hear a humming noise. It's coming from the power supply I'm using. You won't hear it when I demonstrate the prototype motor. It runs from batteries. We'll do that again. I'm now going to simply reverse the polarity to the electromagnet and watch what happens. The magnetism is gone at the face of the electromagnet. Now it's still there at the permanent magnet back here, but simply gone at the face of the coil, thus overcoming what I call magnetic lockup. At 15 volts, we're going to check the maximum force of the electromagnet only. Almost a half, we're at a half pound. Half pound. That's as high as it's going to go. At 15 volts, we're going to check the maximum force of the permanent magnet only. £5. 10 pounds, 11, 11 and a half, 12, 12.75, 13 pounds, 13 and a quarter, 13 and a half, 13 and a half pounds. At 15 volts, we're going to check the maximum force in amplified mode. £10, 15 pounds, 20 pounds, 21, 21 and a half, 22, 22 and a quarter, 22 and a quarter pounds. Okay, notice I've reversed the polarity here. We're going to check at 15 volts the resistance in neutralization mode. There's a half pound, 3/4 of a pound, 1 pound, 1.5 pounds, 2 pounds, 2.25 pounds, 2.5 pounds, 3 pounds, 3.5 pounds, 4 pounds, 4.5 pounds, 5 pounds, 5.25, 5.5, 5.75, 6 pounds, 6 pounds, 6 pounds. At 20 volts, we're going to check the power of the electromagnet only. One pound. Looks like about 1.4 pound. .4 pound. At 20 volts, we're going to check the maximum force of the permanent magnet only. £5, 7 pounds, 10 pounds, 11 pounds, 12 pounds, 12 and a half, 12 and a half pounds, 12 and a half pounds. Okay, at 20 volts, we're going to check the maximum force in the amplified mode. £10, 15, 20, 22, 23, 24, 25, 25 and a half, 25 and a half, 25 and a half. At 20 volts, we're going to check the resistance in the neutralization mode. And note I've reversed the polarity on the electromagnet. 1 pound, 2 pounds, 2.5, 3 pounds, 3.5 pounds, 3.5 pounds, 3.5 pounds, 3.5 pounds. At 25 volts, I'm going to check the maximum force of the electromagnet only. One pound, 1.5, 2 pounds, 2.5, or 2.25, 2.5 pounds, about 2.6 pounds, 2.6 pounds. At 25 volts, I'm going to check the maximum force of the permanent magnet only. £5, 8 pounds, 10 pounds, 11 pounds, 11.5, 12, 12.5, 12.75, 13 pounds, 13.5 pounds, 13.75, 14 pounds, 14.25, 14.25, 14.25 pounds. At 25 volts, I'm going to check the maximum force in amplified mode. Five, 10, 15, 20, 25, 26, 27, 27.5, 27.5, about 27.9, 27.9, 27.9. At 25 volts, we're going to check the resistance in neutralization mode. One pound, 1.5, 2 pounds, 2.25, 2.4, about 2.4, about 2.4 pounds, 2.4 pounds. At 36 volts, I'm going to check the maximum force of the electromagnet only. One pound, 2 pounds, 2.5, 3, 3.5, 4, 4.5, 5 pounds, 5.25 pounds, about 5.3, by 5.3 pounds. 5.3 pounds. At 36 volts, I'm going to check the maximum force of the permanent magnet only. Five, 8, 10, 11, 12, 12.3, 12 and a half, 12.9, 13, 13.2, 13.2. At 36 volts, I'm going to check the maximum force in amplified mode. Five, 10, 15, 20, 25, 30, 32, 33, 34, 34 pounds. 34 pounds. At 36 volts, I'm going to check the resistance in neutralization mode. It's now at 0. Or about 0.4 pounds, I guess. Looks like, yeah, about 0.4 pounds is where it got. 0.4 pounds. That's not much. First, we took 4 readings. Number 1, the maximum force of the electromagnet only. Number 2, the maximum force of the permanent magnet only. Number 3, the maximum force in the amplified mode. Number 4, the resistance in the neutralization mode. The formula for the net maximum force is maximum force in amplified mode minus the resistance in neutralization mode equals the net maximum force. The formula for the percent of power produced from electricity is the maximum force of the electromagnet only divided by the net maximum force times 100 equals the total percentage of the power produced by electricity. The formula for the percent of power produced from magnetic amplification and neutralization is 100 minus the percent of power produced by electricity equals the percentage of power produced by magnetic amplification and neutralization. The formula for the amplification factor is the maximum force in amplified mode divided by the combined forces of the permanent magnet only and the electromagnet only. Here we have the results for each voltage in the magnetic amplification and neutralization test. The gap between the arcs or armature and the face of the electromagnet will change these numbers. The closer the gap, the more force is developed. The gap between the permanent magnet and the electromagnet does the same thing. The main thing is to make sure the net maximum force is sufficient to accomplish your goals. Note the best savings on energy isn't nearest to zero neutralization. The electromagnet is actually being used as a switch, a variable switch, Controlling the flow of electricity to it controls the flow of magnetism coming from the face end of both the permanent and electromagnet combined. Here we have the readings and calculations for the test done at 15 volts. 0.5 pounds was the maximum force of the electromagnet only. 13.5 pounds was the maximum force of the permanent magnet only. 22.25 pounds was the maximum force in amplified mode. 6 pounds was the resistance in neutralization mode. 22.25 pounds max in the amplified mode minus the 6 pounds resistance in neutralization mode equals a net maximum force of 16.25 pounds. The 0.5 pounds divided by 16.25 times 100 equals 3.07% of the power produced by electricity. 100 minus 3.07 equals 96.93% of the power produced by magnetic amplification and neutralization. 13.5 pounds max force of the permanent magnet only plus the half-pound max force of the electromagnet only has a combined force of 14 pounds. The 22.25 pounds of max force in amplified mode divided by the combined force of 14 pounds equals an amplification factor of 1.5. Here's our prototype motor, rather large, but still a motor. At this time, it's operating on 18 volts DC electricity and using the magnetic amplification and neutralization process. Note the electromagnet coils with the permanent magnets attached, along with our wireless armature made of arcs and not a complete circle. For demonstration purposes, I've removed the safety guards that cover the permanent magnets. I'm going to start the motor. Here you can see more detail of the components. Like with the demonstration table, I'm going to explain again the principle of magnetic amplification and neutralization as it applies to this motor. Let's look at the magnetic lockup with no power applied. Now the arcs are going to be trapped between these two magnets and those. No escape. Just like on the demonstration table. I'm going to turn the power on to the motor again, but I'm going to hold the armature to prevent it from turning. Actually, I've installed a stop to prevent it from turning in order to do the demonstration. Okay, now the power's on. You're going to notice it's those coils and a permanent magnet up there are going to really attract it hard. Okay, now I think it takes just over 90 pounds to break that loose up there. Now, these two permanent magnets here and these coils, they're in the neutralization mode. There's no magnetism applied to this end. So when I turn this loose, it's just going to take off like it's going to run. You just saw the motor running at 18 volts DC. Now see what it does at 24 volts. You'll notice quite a bit of difference in the speed, which only makes sense. Now what you're looking at right here is some proximity switches used in conjunction with a timing cam to act as a commutator. Now remember, this is a prototype. In the real application, one would use an encoder along with an electronic motor controller. Now I'm going to start the motor, and you'll see these things start to light up. See, like this one's lit up. This one is activating the coil in the amplified mode. It lights, then goes out, and immediately this one here fires the same coil up in the neutralization mode. Just reverses the polarity. That's all it's doing. And this one does the same thing in line. This one fires it up in the amplified mode. This one reverses the polarity, puts it in the neutralization mode. Just a continuous process. Now I have this little scale here that as you pull tension on it, it'll lock and hold the highest reading. So I want to do the same test on this motor that I did on the little demonstration table. First, at 18 volts, I'm going to check the maximum force of the permanent magnet only. $29.9. The other gauge I had only went to 50 pounds, so I had to get something that was going to measure a lot more than that. So here we have this, and it works the same way. You pull it up and it holds the highest reading, and then you can reset it to 0. So that's what we're going to use on this one. Okay, at 18 volts, we're going to check the maximum force in the amplified mode. Looks like it's 101. 101, I believe that is. I've reversed the polarity in these top two coils and the bottom two coils. There's 4 coils that operate simultaneously on this motor. Now that puts them in the neutralization mode. Now at 18 volts, we're going to check the resistance in the neutralization mode. .35. There where you can see it pretty good. 7.35. At 18 volts, we're going to check the maximum force of the electromagnet only. Now you'll notice I've removed the permanent magnets from the top two coils and the same on the bottom. So we'll check this right here. .4 pounds. 4.4. First, we took 4 readings. Number 1, the maximum force of the electromagnet only. Number 2, the maximum force of the permanent magnet only. Number 3, the maximum force in the amplified mode. Number 4, the resistance in the neutralization mode. The formula for the net maximum force is maximum force in amplified mode minus the resistance in neutralization mode equals the net maximum force. The formula for the percent of power produced from electricity is the maximum force of the electromagnet only divided by the net maximum force times 100 equals the total percentage of the power produced by electricity. The formula for the percent of power produced from magnetic amplification and neutralization is 100 minus the percent of power produced by electricity equals the percentage of power produced by magnetic amplification and neutralization. The formula for the amplification factor is the maximum force in amplified mode divided by the combined forces of the permanent magnet only and the electromagnet only. Here we have the results of the test for the prototype motor at 18 volts. Electric motors run on magnetism. Magnetism that's produced entirely by electricity. Electricity running through copper wire wound around low carbon steel. It's better known as an electromagnet. At 18 volts, this motor gets 95.31% of its energy from permanent magnets. The electromagnets are only used as a switch to turn on and off the magnetism emitted from the permanent magnets and contributes only 4.69% of the energy on which the motor operates. While in the amplified mode at 18 volts, the force of the permanent magnet at the face of the electromagnet is amplified 2.9 times. The higher the voltage, the less percentage of energy comes from the permanent magnets, and the more that comes from electricity. With the proper combination of permanent and electromagnets, I feel great savings could be made on energy. In today's world, early 2009, there's lots of talk about saving energy, electric cars, etc. What if someone installed a motor into an automobile using this technology? What would be the savings? I've heard and read that an electric car gets about 45, now that's 45 miles per single charge of the batteries. If that's so, based on my test results of this technology, I feel that could be increased to as much as 959 miles per single charge. Now that's 45 miles divided by 4.69%, times 100 would equal 959.49 miles. Like with a gas-operated vehicle, it would depend just how heavy one's foot is. Let's say with a heavy foot the efficiency dropped to 50%. That's still 479.7 miles per single charge. I believe with magnetic amplification and neutralization this is possible. Let's consider the other forms of energy used in producing electricity. For every 100 tons of coal currently used, with magnetic amplification and neutralization, that could drop to 4.69 tons. For every 100 barrels of oil currently used, with magnetic amplification and neutralization, that could drop to 4.69 barrels. For every $100 we now spend producing electricity, we could do it for $4.69. Now the permanent magnet just sits there, strong, lots of energy, stays charged, never runs down. You're not waiting on the wind to blow or the sun to shine. Actually, the 4.69% of the electricity needed could probably be supplied by the wind or the sun. You know the old saying, a picture's worth 1,000 words, then I guess a video's worth 10,000 words. The best way I know to describe what you've just seen is in this way. From a young child, I'd heard of the Grand Canyon. Now it sounded really nice. Then I saw some pictures that really looked nice. But that was a long trip from Southwest Virginia and quite frankly beyond my means. When I saw a video of the Grand Canyon, now that made me really want to go see for myself. Well, about 40 years later I did. I'll never forget the first time I stood on the rim of that canyon, looking at that awesome piece of real estate God made. Suddenly I understood why they called it grand. I just stood there in silence. Finally I said, there's no way the pictures I've seen, not even the videos, could capture this awesome beauty. Working on this project, I've often compared it to my first visit to the Grand Canyon. You have to be there. You have to see it in person. Words, pictures, and video just can't fully describe it, can't give you that feeling. You have to see it with your own eyes and feel the effects of this magnetism to really understand it. What I've demonstrated to you in this video, a prototype motor along with some object lesson demonstrations, could be antique in just a few years.